Hey guys, Mr. Ye here again. Today we're covering section 2.6, and if you clicked on this video, you probably saw it's a long one. 2.6 is a packed section, I should say. There's a lot to kind of talk about, but I'm going to do my best to keep it moving, so hang in there, and we're just going to start right off. So 2.6, the section title is Special Functions, and the reason is they're not all going to be perfectly linear. As it turns out, even though we've been talking about linear functions a lot, not all functions are linear, and in the grand scheme of things, not very many are linear, perfectly linear at least, one continuous straight line. So we're going to look at some special families and types of functions today. So if you're looking here, the 5 we're going to cover are the step function, which is on the screen right now. You can see they kind of look like stair steps, hence the name. A constant function, this one is linear, just goes straight horizontally. Absolute value functions, if you ever wondered what absolute value would look like on a graph on a coordinate plane, that question will be answered today. It has that distinctive V shape, V for value. Piecewise functions, which are just functions that have multiple pieces, I guess is the easiest way to say. And so they look a little disjointed and herky-jerky, but we're going to go over those. And then finally, the identity function, which is, unlike the other 4, it's not a family of functions. There is only one identity function, and this is it. So we're going to go through these 5 one at a time, see some examples, work some problems, and then hopefully have a better idea at the end of this video how to tell what kind of function it is, how to graph it, how to write it. So we're going to start with step functions. And as you can see, you know, and we mentioned earlier, they just look like stair steps. They have open dots and closed dots if you look carefully at that graph. And so just reminding you the difference between open dots, closed dots. Open dots mean we do not include that value as part of our solution. And a closed dot means, yes, we do want to mark that value. And so step functions, at first you might look at this and say, wow, this does not look anything like what I will ever need. You know, this doesn't exist in real life. Step functions actually do exist in real life quite a bit. So anytime, and the example that I always jump to is anytime you go buy something and you have to buy them in whole increments, those are kind of step functions saying, I want to buy 1 box of crackers, and so it's $3, and 2 boxes would be $6. I can't really ask for anything in between. I can't say, well, I only want to buy 1.5 crackers, 1.5 boxes of crackers, excuse me. And so 1.5 boxes, I only want to pay the 1.5 box price. No, it's either buy 1, or if you want more than 1, you're going to have to buy 2 boxes. If you want more than 2, you're going to have to buy 3. So what is the domain of this function? Domain, if you remember, is all the x values that we hit. So on this function, and I'm going to take a little bit of liberty and assume that this function keeps going. You know, it keeps stair-stepping up forever, stair-stepping down the other way forever, and that it only showed on this graph what was there. Well, what x values do we hit? We don't hit 0 because it's an open dot, but then we hit everything from 0 to 1, including 1, because it's a closed dot. Then we have an open dot on 1, but we already hit it, so that's okay. Everything to 2. And then everything from 2 to 3. Again, I'm just looking, if we look at each of these stairs and kind of combine where we hit, it looks like we hit everything. And so if we hit everything, then that domain is going to be all real numbers. We've seen a few different ways to write all real numbers, but meaning nothing is left out. We get all the decimals, all the whole numbers, everything. Also worth mentioning is, had we been given the context to this problem, had we been told the scenario that generated this graph, we might say that the domain is, I'll change colors. We might say that the domain is 0 is less than x is less than or equal to 8. And why do I say that? Because that's all that's shown on the graph. Everything from 0, not including 0, all the way to 8. And so if we were given a story problem and it was kind of clear that maybe 0 was the starting point, 8 was the ending point, we might need to write the domain in that way. But without context, I'm just going to assume that this goes on forever, all real numbers. What about the range? So the range is all the y values we hit. And it looks like we hit 60, and then 120, and then 180, and then 240, and then 300, and every time we add another 60, it's a multiple of 60, but we don't hit anything in between. We don't hit 241 or 242 or 243. We always just jump up by 60s. So I'm going to go back to that set builder notation that we've seen before. And I'm going to write that our range is the set of all the y's such that y, I'm gonna adjust this, sorry. All the 60 times y's such that y is an element of the integers. Gosh, I forgot my y. Y is an element of the integers. Okay, parsing this through, reminding you, because I know we haven't done a ton of set builder notation, just mentioned it a couple times. What this says is that the range is the set of anything we can get by multiplying 60 times y, where y is any element that is an integer, that is a whole number. Again, this is assuming that the graph keeps going up and down forever. So by saying this, we're saying, well, if y is 0, then 0 is part of the range because 60 times 0 is 0. If y is 1, then 60 is part of the range because 60 times 1 is 60. If y is 2, then 120 is part of the range because 60 times 2 is 120. And that's the way that we can get all multiples of 60 and nothing else. Okay? So let's look at the best known, most well-known step function, and that's called the greatest integer function. You will see this on your practice problems. It has this double square bracket that's not a typo. That means it's the step function, the greatest integer function. And what this is the greatest integer that is less than or equal to x. So for example, I'm going to put a 0 there. And I'm going to draw a number line up here because I like looking at number lines with these. What is the greatest integer that is less than or equal to x? Well, if x is 0, the greatest integer is 0. We've gotten to 0, but we haven't quite gotten to 1 yet. What if x is 0.5? We've gotten to 0. We still haven't quite gotten to 1. The greatest integer that we've gotten to is 0. What if x is 0.99? Well, then the greatest integer we've gotten to is still 0. We haven't gotten to 1 yet. As soon as we get to 1, we jump up to 1. And 1.7 will still be 1 because we haven't gotten to 2 yet. And 1.99 will still be 1. But the second we hit 2, we jump to 2. And so by doing this, you can see the pattern kind of quickly. 2.4 will still be 2. 2.99 will still be 2, and then it will jump to 3. So I'm going to start plotting this on my graph. 0 was 0. 0.5 was 0. 0.99 was 0. So we go all the way until we hit 1. I'm going to put an open dot on 1 to say we want to go all the way up until 1, but not actually 1. And then we jumped at 1, we jumped up to 1, and it stayed 1 until we got to 2. And then it jumped up to get 2. And we can see this pattern forming, and we don't have to make our table forever because we see it's going to keep jumping by 1, last for 1 unit in the x direction, and then jump. Now, I like to always start in the positive x direction, and I highly recommend you do the same, because here's where it gets a little tricky. Negative 0.2. Here's my number line. Here's negative 1. So negative 0.2 I'm looking at is about right here. What is the greatest integer that is less than or equal to that dot that we've gotten to? We haven't gotten to 0 yet. We have to fall back to -1, which blows the theory out of the water that some of you might have had in mind of, well, let's just always chop off the decimals. Let's just keep that whole number part. It works in the positives, not in the negatives. So I always start on the positives, find my pattern, and then just fill in the negatives on my graph. That is how we will be graphing these greatest integer functions. Really quickly, what's the domain? Domain looks like all real numbers because we're able to plug in anything and it goes forever and ever and ever. What is the range? I'm going to say y is an element of the integers. There's that fancy looking z again that stands for integers. Y is an element of the integers means I hit every integer, every whole number, positive and negative, but nothing else. So that'll be my range. So here's what I'm going to ask you to do is our last problem in the step function before we move on to the next one is it has to do with recycling. A recycling company pays $5 for every full box of newspaper. They do not give any money for partial boxes. Draw a graph that shows the amount of money for the number of boxes brought to the center. What is the domain? What is the range? And then is it a function? This is a hard problem. This is a tough one, but I want you to pause the video and you don't have to do it necessarily, but think about it, process it, see what will that jump be? You know, if we buy in half a box, we get nothing. If we bring in 1 box, we get $5. What happens if we bring 1.5 boxes? What happens if we get 2 boxes? Think about that. Pause the video and 30 seconds, 60 seconds, come back and we'll work this out. All right, now that you've had a chance to think about this problem, let's get going. I've already started drawing a table on that left-hand side. I'm making my X's the number of boxes I bring in, and the Y's how much money I'm going to be paid for those boxes. If I bring in 0 boxes, $0. That's the way the world works. If I bring in half a box, we were told above they do not give any money for partial boxes, so I'm still getting $0 for that half box of newspaper. What if I bring in 0.99 boxes? You'd like to think in the real world, someone would say, yeah, that's about 1 box. But according to these rules, we're still getting nothing. That's still a partial box. 1 box, I get $5. What about 1.99 boxes? That's just 1 in a partial, which I don't get any credit for. I'm still only getting $5. 2 is when I jump up to 10. 2.8 would still get me 10, but as soon as I hit 3, I'm jumping to 15, and I can see the pattern now. Always try some decimals when you're dealing with this greatest integer step functions. So 0, 0, and it stayed 0 all the way until 1. Looks kind of familiar. But then once I hit 1 box, 1, 2, 3, 4, 5, I need to jump up to $5. I'm making $5 for bringing in that box, that full box of newspaper. $5, I'm going to stay at $5 according to my table until I get to the 2 box mark. And then 1, 2, 3, 4, and I'll call it right here. And it's jumping by 5 every time, which makes a lot of sense because that's the situation, right? I get $5 more every time I complete another box. So this is what the graph would look like. I'm not going to fill in the negative side because this is one of those word problems that I was mentioning earlier. It doesn't really make sense for me to bring in negative boxes and try to get paid for it. So I'm just going to leave it on the positive side, and that will affect my domain and range. Domain looks like all the x's greater than 0. So I'm just going to write that instead of set builder notation. I'll say all the x's greater than or equal to 0. I could bring in 0 boxes, but I'm hitting everything. I'm not skipping anything. I went all the way from 0 to 1, and then I went all the way from 1 to 2, 2 to 3, and I can, in theory, bring in as many boxes as I need. What about the range? Well, the range is the set of all the y's, and I should say all the 5 y's because I want multiples of 5, such that y is an element of, and I'll say element of the integers and that y is also greater than or equal to 0. And let me explain that. I don't want to include negative multiples of 5 in my range, because we said negative doesn't really mean anything in this case. So I'm going to say just the integers that are greater than or equal to 0, those are our y's that we will be multiplying by 5. And so that gets me this range. Last question, is this a function? Answer is yes. It passes the vertical line test. I know it's all broken up and stuff, but if I draw a vertical line anywhere, I'm only ever going to hit it once. That was an awfully curved vertical line. I will try a little bit better, not much better, but I'm only going to hit the function once. So it passes the vertical line test. Yes, it is a function. Guys, step functions are maybe the trickiest, definitely one of the trickiest ones we're talking about today. But hopefully this gives you an idea, and now you know when you look at your practice problems what this double bracket means. It means that greatest integer function. So let's go on to one of the easier ones then. One of the easier functions we're looking at is the constant function, and we've kind of seen this before. It's just a horizontal line that goes all the way across your graph, never goes up, never goes down. And so it's always written like this: f of x equals some number. In this case, f of x equaled 3, because that's where my horizontal line was. It could be f of x equals -1, and that would get this perfectly horizontal purple line that I just drew. So horizontal lines are constant functions is what they're called, because the y value stays constant. Why are vertical lines not constant functions? Well, because they're not functions. Because they don't pass the vertical line test. I would hit infinitely many times on a vertical line. And so they are not functions. That's the reason they are not constant functions. What is the domain of the blue line on the left? Domain, it's going to the left forever, right forever, all real numbers. How about my purple line? All real numbers. Every constant function will have a domain of all real numbers. What about the range? Blue line's range is y equals 3. Because that's the only y value we're ever going to hit, even if we keep going and going and going. So by that logic, what is the range of the purple line? Y equals -1. That's the only y value we hit. So constant functions, horizontal, domain is always all real numbers, range is just that value because that's the only y value we are going to hit on this graph. And that's all we need to say about constant functions. I told you that one would be quicker. We start with those step functions, and they're kind of tricky. They take a while. Okay, the third one, the identity function. This is just good for you to know, important for you to know. The identity function is not a family. Constant functions, we can have any number of constant functions depending on where it is on the graph. The identity function is just one single function, and it's right here. F of x equals x. So first question, why is it called the identity function? Well, because x and y always share an identity. When x is 0, y is 0. When x is 1, y is 1. When x is 4, y is 4. And so they share that identity, and so that's why it's named the identity function. But notice also that we could write it as f of x equals 1x plus 0. To put it in slope-intercept form, which you may or may not be more familiar with. 1x plus 0, slope of 1, y-intercept of 0. It's this diagonal line going uphill straight through the origin. What's its domain? Well, it's going left and right forever and ever and ever. All real numbers looks good. What about the range? The range, well, it's going up forever and it's going down forever and it doesn't skip anything. Range of the identity function is also all real numbers. Okay, so identity function is another quick one. Domain, all real numbers, range, all real numbers. It always is just that diagonal line, slope of 1, going straight through the origin. 3 down, all of a sudden, 3 down, 2 to go. Let's talk absolute value functions. So absolute value functions always have this very distinctive V shape. Sometimes the V is really wide, sometimes the V is narrow, sometimes it's upside down, really wide, really narrow. It might be moved off to the side, but it always has this V shape. And so how do we graph it? we want to find the rebound point, and I'll talk about what that is. That's kind of this point, that's my own term. If you tell that to another math teacher, they probably won't know what you're talking about. But where it's going down, 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 and then it rebounds and starts going up. So it's the base of the V. Find that rebound point, and then just plug in a few values on either side till you get your V shape. So we're going to be making tables for these, and we'll do a couple problems. What is the domain of this function on the screen? It goes left forever. It goes right forever. It doesn't skip anything. All real numbers. Range is not all real numbers though. What is the range? Well, the range, it looks like we hit everything 0 and above. So I could say y is greater than or equal to 0. I never went down, I never went into the negatives, and it has to do something with the absolute value function, always being positive. So that's the domain for this one, the range for this one. Is this a function? Vertical line, I'm only hitting once. No matter where I go, I only hit once. Yes, this is a function. Okay. Let's try one from scratch. So right here, we've got absolute value of x minus 3, and I want to graph it and find the domain and range. I need a table. But to know where I want to kind of center my table, I need to know the rebound point. Here's how we do that. I'm going to take whatever is inside the absolute value and set it equal to 0. And then solve for x. So add 3 on both sides, x equals 3. That is my rebound point. When we set whatever's inside the absolute value equal to 0, and then solve for x. So I now know I want to start my table in the center at 3. So my y value, 3 minus 3, absolute value of 0 is just 0, 3 comma 0. Let's try plugging in 4. So absolute value of 4 minus 3 equals absolute value of 1, which is just 1. Now, I'm going to plug in 2. I'm going to plug them in on either side. What is the absolute value of 2 minus 3? Absolute value of negative 1, well, that's also 1. And we can totally see our rebound point and our absolute value V starting to form. I'm going to do just a couple more. So this is negative 2, 1 minus 3, but absolute value turns it to positive 2. 5, I'm just going to write 2. And I'm okay if you do this. Absolute value graphs are symmetrical around the rebound point. So if you found that rebound point, and you plug in on one side 1 away, you know the other side 1 away. If you plug in one side 2 away, you know the other side 2 away. And this is how we get our absolute value graph. Range, start with domain. Domain, all real numbers. We go forever to the left, forever to the right. We don't skip anything, all real numbers. What about the range? What y values do we hit? Well, again, it looks like anything greater than or equal to 0. It will not always be like this. Simple examples, this is how we start. But it will not always be like this, but you just look at your graph and say, well, I hit 0 and I continue to hit everything above as I do this. So all my y's above 0 are taken care of greater than or equal to 0. I'm going to start this next one with you and then let you try it. This one's a lot more complicated. Graph, f of x equals negative 2 times the absolute value of x plus 2 plus 4. First things first, we need ourselves a table. We need to know what the rebound point is. So I'm going to take whatever's inside the absolute value, set it equal to 0, solve for x. X equals negative 2, I now know is my rebound point. So let's plug in and find what we'll get for y then. So we get, I'm just going to plug it into the function, negative 2 times absolute value of negative 2 plus 2 plus 4. So negative 2 times the absolute value of 0 plus 4. Negative 2 times the absolute value of 0 is going to be 0. So we get negative 2 comma 4. And that should be my rebound point. Here's what I want you to do. choose either -3 or -1, plug it in, see what you get, and then plot it on the graph. Remember, it's symmetrical, so once you have one, you can get the other. Then plug in either 0 or -4. I know which one I'm going to pick, which one's probably easier. See what you get, plot it symmetrically, and then at that point, once you have 5 points, you can usually draw in your V and find the domain and range. So that's what I want you to do right now, is try finishing out this problem, and then once you're ready, go ahead, click play, and see kind of what it looks like from my end. All right, so I put some of my work on the screen. You can see I plugged in -3 and simplified, and it took a little bit of simplifying, but eventually I got where x is -3, y will equal 2. Plotted that on the graph, and then you can see down here, since I knew -3, which was 1 away on the left from my rebound point, I can just use that same value for 1 away on the right rebound point. So -1, 2, plotted it on the graph. I plugged in 0 and worked it out, and it took a little bit, but eventually I saw that when x is 0, y should be 0. Plotted it on the graph, and since I went 2 to the right and got 0, I knew I could go 2 to the left and also get 0, -4, 0. Had my 5 points, drew my absolute value. There we are. What is the domain? Domain, all real numbers, going left forever, going right forever. No skipping. But what is the range here? What y values are we hitting? Well, it looks like we're hitting anything at 4 and below. We're hitting everything 4 and below. So I'm just going to write that. I'm going to say y is less than or equal to 4. And that's my domain and range on this problem. Because I'm somewhere on the graph, I'm hitting every y value that is less than or equal to 4. So absolute value functions, find your rebound point, make your table, find your V shape, and then state that domain and range. The last special kind of function that we are looking at today is called a piecewise function. These are some of my favorites because they're just broken into multiple pieces. It's almost like 2 functions for the price of 1, except that each function only covered half the graph. So look at the graph on the screen right now. And I'm going to write out what this piecewise function looks like. You'll notice I put a big curly brace, f of x equals, this is going to indicate it equals multiple things, different spots of the graph. So first I'm going to look at this leftmost part, this green part right here. So it has a y-intercept of 1, 2, 3, -4. So b equals -4. It looks like m equals -1. It's going over 1, down 1, over 1, down 1. So this graph looks like f of x equals mx plus b, -x minus 4. So I'm going to write that. F of x equals -x minus 4, but I'm going to put a comma. And I'm going to say this is only true when x is less than 2. Because if you look at it, here's my dividing line where the function kind of breaks, and that's at x equals 2. So everything to the left of it is going to use this rule to get that green and now highlighted in yellow part of the graph. Everything to the left of that line. So when x is less than 2, that's my line. What about when x is greater than 2? Well, this is our constant function. We saw this one earlier, y equals 1, or f of x equals 1. I'll stay consistent. F of x equals 1. So I'm going to say f of x equals 1 when x is greater than or equal to 2. So when x is greater than or equal to 2 on the right side of that yellow line, I'm just going to use that definition, f of x equals 1 the whole time. I did put equals because it had a closed dot. I don't think I've said that yet. Guys, this is what piecewise functions are. They're just different parts of the graph have different function definitions. What is the domain? Well, on this one, it looks like it goes forever to the left, and I come back and I've hit everything so far. I didn't hit 2 because it's an open dot, but then it's a closed dot up here, so I did hit 2 really, and I keep going forever. It looks like the domain is all real numbers. And you're starting to see, if you have no idea on an SAT or something, all real numbers isn't a terrible guess. A lot of functions have all real numbers for their domain. What is the range? This one's a little bit trickier. I'm going to say that the range is y is less than -2 or y equals 1. And it's okay to write it kind of in English like this. How did I get these values? Well, because I'm hitting every y value that is less than -2 based on this part. It's going down forever. That's what that arrow on the left means. But then I don't hit -1 or 0 or 1, or I do hit 1, excuse me. I don't hit anything in this region until I get to 1. And I don't hit anything above 1 either. So y is less than -2, that takes care of the green ray, or y equals 1, that takes care of that magenta ray. Is it a function? Yes. Vertical line test, you can visualize it. You can only ever hit it once, that makes it a function. All right, last problem of the day. I know this has been a long video. Thank you for sticking with me. Last problem of the day. What if we are given the piecewise function definition and we need to graph it? So here's how we're going to do that. I'm going to look at it step by step, just like we did before, now just going in reverse. So f of x equals -x when x is less than or equal to 3. I know what -x looks like. That's -x plus 0. So that means I'm going down 1, down 1 over 1, down 1 over 1. I almost made it a positive x. But I'm going this downhill line, -x, forever and ever when x is less than or equal to 3. So I'm going to get my 45-degree angle and say, okay, 3 is where this thing starts or stops, depending on how you want to look at it. That is the leftmost ray of this graph. Whenever x is less than or equal to 3, we should use -x as our definition. What about here? When we're between 3 and 5, it says f of x just equals 2, another constant function. So I'm going to put open dot on 3 because it was less than 3. I'm going to put closed dot where x equals 5. And I'm told it's just this horizontal constant function line. F of x equals 2. What about the final one? F of x equals x plus 1, but only when x is greater than 5. So this one, here's how I like to do it. I like to say, okay, well, then I'm gonna make a quick table for this magenta. X, f of x. When x is 6, for example, I need to do 6 plus 1, so 7. When x is 7, I need to do 7 plus 1, so 8. And I can really spot it. So when x is 6, 1, 2, 3, 4, 5, 6, I should be up at 7. 4, 5, 6, 7. 7 is 8. 8 will be 9. And how long does this continue? Well, it starts at x equals 5. Right past it. I'm going to put an open dot because I don't want to include x equals 5 in this part of the function definition. But I'm just going to draw that ray and step back and look at my piecewise function. 3 pieces, 3 different pieces for 3 different kind of parts of the graph. We just graph them one by one in their respective zones. What is my domain? Well, looking at x's, I've covered everything to the left all the way through here, and I have a closed dot, and then I go a couple more for that next part, and then I do everything to the right. It looks like domain is all real numbers. What about range? Domain, there were no gaps in the graph in my x direction. What about range? I mean, range, it looks like I'm hitting everything above. This is -3. So it looks like I'm hitting everything above -3 with this part. And I'm also hitting 2, and I'm also hitting everything above 1, 2, 3, 4, 5, 6. So everything above -3, 2, and everything above 6. Good news is we don't have to write all of that. We don't have to write y is greater than or equal to -3 or y equals 2 or y is greater than 6. We don't need to do that because if you think about it, all of those are actually taken care of by the very first one. Y is greater than or equal to -3. Does that include 2? Yep, 2 is. Does that include everything above 6? Absolutely. And so we were able to just write the range. We're hitting everything above or equal to -3. One last glance, it is a function. I never hit more than once. And you might be wondering, wait a second, hold on. What about right here where I hit these 2 dots? You are correct that we hit 2 dots. But one of them's closed, which means we actually hit it. One of them's open, meaning it's not really a part of the graph. We just pass right through it. So we still only hit once. Vertical line test is passed. This is a piecewise function. Your other clue that it was a function is that it has function in the name. So, guys, this was a long video. We talked about step functions, took a long time. Constant functions did not take a long time. Identity function was really quick. Absolute value was medium, V-shaped. And then these piecewise functions, graphing them or writing their definitions, just multiple parts of the function in different parts of the graph. So I'm hoping this was helpful. This was a loaded section 2.6. If you stuck with me, thank you. If you had to divide this up into two viewings, understandable. But any questions you have, this is some kind of tough stuff. Any questions you have, write them down so that when we're going through this together, you can ask those questions. Guys, almost done with chapter 2. We'll be talking about 2.7 in the next video. Hopefully this made sense. Let me know if it didn't. And until next time.